Welcome you all for the discussion of functions, the prerequisite concept of infinite series. So from the basics of functions, we shall then move on to sequences and then let us discuss infinite series. Okay, what do you mean by a function? Let us start with the definition. So function, when we say that function, generally this comes to our mind. F colon A arrow mark B. So what are these A and B? What is this F? Okay, let us discuss along with the definition of function. So this is the definition of function. A function, generally denoted by f, is a rule, it is actually a rule that assigns unique element of a set to each element of the other set. So this is the definition of function. See, if I write f colon from A to B, then this f, which is called as function, it represents a set of rule that maps the elements of A, that maps every element of A. That point is very much important. Every element of A to a unique element of B. So function is a rule that maps every element of A to a unique element of B. So this A, from which the function is picking the elements or members, is called the domain. Where from we are taking the members is called the domain. This set B, to which the elements are mapped, is called codomain. So function is a rule that carries all the elements of domain to unique element of codomain. Let us illustrate with a simple example. Here I am considering the example. I have two sets A and B. This A is a set of first 5 natural numbers and B is the set of first 5 English alphabets. And I am assuming that 1 is mapped to A and 2 is mapped to B, 3 is mapped to C, and similarly 4 and 5. So F is a mapping or function that carries 1, 2, 3, 4, 5 to A, B, C, D, E respectively. So if I say F carries 1 to A, then I should denote that. So to denote that, this is the notation. F of 1 equal to A. So meaning of that is 1 is mapped to A under F. Okay. Or we say that A is the image of 1 under F. So there are two ways. Either you can say 1 is mapped to A under F or A is the image of 1 under F. Similarly, if I write f of 2 equal to B, means that B is the image of 2 under F, or you can say 2 is mapped on to B under F. So in both the way we can say. Similarly, you can write f of 3 equal to C, f of 4 equal to D, f of 5 equal to E, and so on. See, generally, if we have a set A and B and F is a mapping from A to B, then that function is denoted within flower brackets. You can write f of A belongs to A. So this is one way of representation of a function. Or another way of representation, you can write set of An. N belongs to a set of natural numbers. So this is preferably when the domain is the set of natural numbers. Otherwise, this notation is more convenient. For example, you can take as an example I am taking. Suppose R is mapped to Ramesh. I'll just write Ram. And A is mapped to Anand. B is mapped to Balu. In such case, we cannot use this notation, but we can use this. This is the set of all f of A such that A belongs to A. So then this is actually, if you expand this, here you have to write f of A You have to choose next element of capital A. Here after A you have B. F of B. See, here I have written small letter, here I have written capital letter. Whatever that may be. Here you have to just pick elements of this set. That's all. Nothing to worry whether it is small letter or capital letter. Then F of R, which actually represents the second set. So this is one way of notation, and second way of notation is this. So when we can use this notation, as I said already, if the domain is set of natural numbers, then we can use this notation. For example, here I can write a1 equal to a, a2 equal to b, a3 equal to c, a4 equal to d, and a5 equal to e. So this says 1 is mapped onto a, 2 is mapped onto b, 3 is mapped onto c, 4 is mapped onto D, and 5 is mapped onto E. There are various notations to express the given function. You can use the convenient one. So next, let us take some more simple examples of functions. See, let us restrict our discussion for set of natural numbers. That means I am restricting the domain A to be set of natural numbers. Set of natural numbers means 1, 2, 3, 4, 5 and so on. So these numbers are called set of natural numbers. So the general notation is capital N. Okay, let us write some simple examples. If I write f of n equal to n, then it is a functions of all natural numbers. Similarly, you can define f of n equal to 1 for all n. So this is called constant function. If you define f of n equal to 0 for all n, then it is a zero function. Similarly, you can have different types of functions. So here, the most important thing is how to understand the definition and notation of functions. That is very much important. If the domain is restricted to set of natural numbers or subset of set of natural numbers, subset means this is the collection of all natural numbers. You have to take some of the elements from that set. For example, you can take a1, okay, a dash to be 5, 10, 15, 20, 25. See, this is collection of some natural numbers. So it is subset of n. So now I am assuming A to be either set of all natural numbers or some subset of natural numbers. So any function defined on A is called a sequence. So this is the definition of sequence. A function in which the domain is restricted to set of natural numbers is called a sequence. So sequence ಜನರಲ್ ಆಗಿ ನೀವೆಲ್ಲ ನೋಡಿರ್ತೀರಾ ಅಥವಾ ಆ ವರ್ಡು ಯೂಸ್ ಮಾಡಿರ್ತಾರೆ. ಸೀಕ್ವೆನ್ಸ್ ಅಂತಂದರೆ 1 by 1 ಅಂತ ಜನರಲ್ ಮೀನಿಂಗಲ್ಲಿ ಇರುತ್ತೆ. ಸೊ ನಾವು ಮ್ಯಾಥಮೆಟಿಕಲ್ ಆಗಿ ಅದನ್ನು ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡೋಕೆ ಹೋಗ್ತಾ ಇದ್ದೀವಿ. ಸೊ ಸೀಕ್ವೆನ್ಸ್ ಮೀನ್ಸ್ ಇಟ್ಸ್ ಎ ಫಂಕ್ಷನ್ defined on set of natural numbers. Let me take these examples again. See, if you write f of n equal to n, then it is a sequence of natural numbers. Earlier I just had the word functions, right? So sequence of natural numbers. F of n equal to say 2n, it is a sequence of even numbers, strictly speaking even natural numbers. So similarly, if you take f of n to be 2n plus 1. Let me take f of n to be, I'll write here 2n plus 1. Set of all, I mean sequence of odd numbers, sequence of odd natural numbers. Similarly, you can define f of n equal to n square, sequence of square numbers. Okay, this is how the sequence is defined. Sequence is the function defined on set of natural numbers. Okay, then I hope you got the idea of sequences. Let me see some examples of sequences. Then we shall move on to infinite series. Okay, let us take some examples. Next, examples. Okay, examples. Let f of n equal to n square, okay, n square plus n. Then f of 1 is 2, f of 2 is 2 square plus 2, 4 plus 2, 6, f of 3, it is a 3 square plus 3, 12, f of 4 equal to 4 square plus 4, 20, and so on. So it is a sequence. So I can write like this: 2, 6, 12, 20, and so on. So it is a sequence. It is an example of a sequence. Even since the domain is restricted to set of natural numbers, I can denote this A1, this A2, A3, A4, and so on. I can represent this set by writing AN. This is a simple example. You can take one more example. Say this is example A, and say example B. You can take f of n equal to 1 by n, right? Then the corresponding sequence is 1, 1 by 2, 1 by 3, 1 by 4, and so on. It is a sequence of reciprocals. Okay. Similarly, we may have many such examples. So this is the definition of sequences. So functions, that is a rule defined between two sets that carries each element of one set to a unique element of the other set. And if the domain of a function is restricted to set of natural numbers, then such function is called a sequence. Next, we need to define series. I'll just write here. What is a series? See, for the definition of a series, we have to start with the sequence. I have a sequence AN. Now I'll define an expression of the form, un equal to summation of ai ranging from 1 to n is called a series. So this is mathematical definition of series. Let me see what is this series is actually. Let us take this example itself. Or okay, let us start with the sequence of natural numbers. Suppose f of n equal to n. I can write this as an equal to n, right? Then a1 is 1, A2 is 2, A3 is 3, and so on. An is n generally. Then see, using this definition, so un equal to summation ai means un equal to a1 plus a2 plus a3 and so on plus an. Now u1 equal to 1. I am restricting myself to this example. U1 is 1, U2 is 1 plus 2, that is A1 plus A2. U3 is 1 plus 2 plus 3. U3 is, U4 is 1 plus 2 plus 3 plus 4. Similarly, un is, for this particular example, it is 1 plus 2 plus 3 plus and so on n. So this un is called a series. This is called a series. See, it is a set of numbers connected by plus sign. Series is nothing but a set of elements connected by, generally it is numbers. So a set of numbers connected by positive sign. This one. So this is a strict definition, mathematical definition for series. So series is always defined along with the sequence. If I have any sequence, then an expression of the form summation ai, ranging from 1 to n, is called a series. Then we saw an example of a series. This is one of the example. If this sequence is 1, 2, 3 and so on, then the corresponding series is this one. Let me take the second example. Let us start with this example only. Second example. I will take this example itself. Here u1 is 1, u1 is equal to a1, that is 2, u2, that is a1 plus a2, so it is 2 plus 6, u3 a1 plus a2 plus a3, that is 2 plus 6 plus 12, u4 a1 plus a2 plus a3 plus a4, that is 2 plus 6 plus 12 plus 20. Similarly, you may define u5, u6, u7 and so on. So here we will have two types, finite series and infinite series. So how to define finite series and infinite series? If a series, if a series involves finitely many terms, then it is finite series. Very simple. Finitely many terms, then it is finite series. See, the finite or infiniteness of a series depends on the corresponding sequence. As I said already, we will define a series depending on the sequence an, that ultimately depends on this sequence. If this sequence contains finitely many entries, then the corresponding series will be finite series. Or simply, you can say that a series un is finite if it contains only finitely many terms. Otherwise, it is infinite. Then, after the definition of finite and infinite series, we had to define some more simple parameters. If each an is greater than or equal to 0, generally, strictly speaking, we will take an strictly greater than 0, but even if you take an greater than or equal to 0, then you get the same thing. If an is greater than or equal to 0, then the corresponding series un, that is summation an, is called series of positive terms. It's called series of positive terms. As I said already, the last two examples both are series of positive terms, because see, u1 is greater than 0, greater than 0, greater than 0, greater than 0. So if each term of the sequence an is greater than or equal to 0, then the corresponding series summation an is called series of positive terms. Similarly, you may define series of negative terms, and there are some series which are neither positive nor negative. If you take an to be minus 1 power n, then an, the entries of this sequence are minus 1, plus 1, minus 1, plus 1, and so on. So then the corresponding sequence, corresponding series, u1 is minus 1, u2 is minus 1 plus 1, so 0, u3 is minus 1 plus 1 minus 1, u4 is 0, and so on. So it involves minus 1 and 0. So we cannot strictly say that this is series of negative terms, because 0 you cannot say neither positive nor negative. So to avoid such confusion, we'll remove this equality sign. So it is strictly greater than 0 or strictly less than 0. If an is strictly greater than 0, then the corresponding series is called series of positive terms. If an is strictly less than 0, then the corresponding series is called series of negative terms. So then we have one more parameter. So given a series, let us start with the sequence. I have a sequence an, and corresponding to that I have a series un equal to summation an. So here summation an means I am just adding first n terms of the sequence. I am just adding first n terms of the sequence. So given any series, the sum of first n terms is denoted by Sn, called sequence of, or okay, let me take this sequence word later, otherwise you will be under confusion, because I moved from sequence to series, then again moving back to sequence. So Sn is called nth partial sum of the given series. Sn is called nth partial sum of given series. So you might have get confusion here. See, Sn is the sum of first n terms, and here I got u2, sum of first two terms, u3, again sum of first three terms, similarly. So to just try to clarify yourself here, this u1 is nothing but s1, because you are adding first term, that is, there is only one term, nothing to worry. a1 plus a2, that means you are adding first two terms, so this is nothing but s2. So for these particular examples, whatever I have taken so far, for those two examples, you have these to be S1, S2, S3 and so on. There is no much difference between U1, U2, U3 and S1, S2, S3 for these particular examples. But in general, if you have any series Un, then Sn represents sum of first n terms. Okay. Then we need to discuss the major parameter, convergence and divergence of the given series. So let me discuss that concept in the next video. And with this discussion, I am ending up this video. Hope you understand what you mean by a function, sequence and series. So next video we shall have the discussion on convergence and divergence of series. Thank you.